Welcome back. So, this is lecture 10 in this course on mathematical tools. The topic I have given to this lecture is applications of logarithmic and exponential functions. So, now these two functions have some important applications and we use them very often in cognitive science research. But before I discuss the applications, let us try a couple more problems on logarithmic and exponential functions, and then we can go on and discuss applications, right. So, first problem is this, what if I give you an identity on logarithmics. So, let us say this is the identity, log of x into y equals to log of x plus log of y, okay. And your goal is to prove this identity. Okay. So, prove this identity. Does this identity hold? So, you need to prove this. You have seen this identity before. I want you to prove this identity. You are given identity about exponents. Okay. So, this was one of the identity on exponents, e to the power x y equals to e to the power x plus y equals to e to the power x into e to the power y. Okay. So, this was one of the identity on exponents, and you are also given that, let us say, e to the power log x can be written as x, okay, or log of e to the power x can be written as x. Here, of course, in this case the x has to be greater than 0. Here you do not have that constraint. Okay. So, let us try to prove this logarithmic identity using this rule of exponent and using this idea that exponent of log or log of exponent is x, basically the inverse function idea. Okay. So, let us see. If you try to directly start with this identity on exponents, e to the power x plus y equals to e to the power x into e to the power y, and if you try to take log on both sides, okay, which you can do, no problem in that. So, I am taking log on both sides, okay, but it will only make you reach here, x plus y equals to log of e to the power x into e to the power y. Now, you will get stuck because you are not getting the desired form here, you are getting x plus y. But if you see in this identity, what we really need is at least x into y. Okay. So, we do not need this term x plus y. Okay. So, we need some term which has x into y, not x plus y, right. So, you cannot go any further with this approach, and you won't be able to reach the logarithmic identity. Okay. So, you should not take this approach. Okay. So, you can always visualize that whether this approach would go any further or not. We are not getting any term in the desired form, so it will not help you. Okay. You can take some other interesting approach. So, here you have, so this identity is a generic identity, e to the power x into e to the power y equals to e to the power x plus y. This is your identity, right. This identity would hold for any function. Okay. So, let us say if you apply to f of x into e to the power g of x or whatever g of y, okay, still you can write f of x plus g of y. Okay, that is not the problem, this identity would hold, right. So, this holds for any variables x and y. So, what if rather than f of x and g of y, I write e to the power log of x into e to the power log of y, okay, on this side. And what I write, then what would be my right hand side? It would be e to the power log x plus log y. Okay. So, this is the form I am getting. Now, I am getting closer to the identity, because in the identity I have something like this. And here, because you have e to the power log x, e to the power log y, right, this actually, this thing is e to the power log x can be written as x, and e to the power log y can be written as y. Of course, x and y should be greater than or equal to 0. That is the only constraint here. And this should be equal to e to the power log x plus log y. Okay. This can also be rewritten as e to the power log of x into y. Okay. Or in other words, or in other way, if you take now log on both sides. So, if you take log of x into y and log of e to the power log x plus log y, okay, we are taking log of this exponential function on the LHS on the left hand side, you can just keep writing log xy. Here log of exponential function would become log of x plus log of y. So, basically you are just writing this exponent term, right. Now, we have got our identity log of xy equals to log x plus log y. Okay. This is how we can prove this identity. Now, there is some homework for you. So, what if I want you to prove this identity? Prove this identity that log of x to the power m equals to m log x. You need to prove this identity. You can take the same approach as we took here with the exponents with the previous identity and try to prove this identity. Okay. This is something you can do at home. Okay. Good. Now, let us try some more exercises on logarithmic and exponential functions. Let us say some equations which have both logarithmic and exponential functions. Okay. So, let us say you have something like log x square plus 2 equals to 3 log x. Okay. Can you solve this equation? Let us try some more. Log x square plus log x square plus 1 equals to, sorry, let us say plus log 1 by x square plus 1 equals to 0. Okay. So, we try one more. Let us say this is a to the power log x plus 2 plus log 1 by x plus 2 plus x equals to 3. Okay. So, let us begin with problem number 1. These are in class exercises. So, as before, you can stop the video and try to solve these problems before you see the solutions. Let us begin. Log x square plus 2 equals to 3 log x. So, our goal would always be to simplify the terms that look slight bit complex. Okay. So, in the LHS the terms look slightly complex. This has some x to the power something, right. We do not want x to the power something, we want to simplify it as much as possible. Okay. So, it is log x square. Can we simplify this? Yes, we can rewrite as log 2 log x plus 2 equals to 3 log x. So, here you have 2 log x, here you have 3 log x. Now, you can operate such that you take 2 log x on this side. So, 2 would become equal to log x. That means x equals to e to the power 2 e square. Okay. So, we solved it for x. Let us try the second one. Now, second one is slightly tricky. So, you have log x square. So, square of the entire thing, log x function. Then you have log of 1 by x square. Then you have 1 plus 1 equals to 0. Okay. Now, interestingly, you do not know a way how to simplify this. This is a square of entire thing, not the square of x. If it would have been log x square, you could have written 2 log x, but now this is a square of the entire thing, log x. So, we do not know how to solve this. So, let us keep it as it is for now, log x square. Here you can simplify. So, you can rewrite this term as log of x to the power minus 2 plus 1 equals to 0, and we can simplify it even further. Sorry, log x square. Okay, so log of x to the power minus 2. So, you can rewrite it as minus 2 log x plus 1 equals to 0. Now, this equation has some form. Okay, you might remember this form. This is actually the expansion of log x minus 1 whole square. Okay, you can try this log x. So, a minus b whole square. So, a square minus 2ab plus b square. So, this is expansion of this term. So, you can rewrite this term as log x minus 1 whole square. Okay. This is how you can rewrite. Of course, x has to be greater than 0, that is a constraint, that is still valid. Now, this thing is equal to 0. So, that means log x minus 1 equals to 0, and that means log x has to be equal to 1. So, in what situation log x would be equal to 1? Well, when x equals to e or whatever base you have. So, that is the solution for this. So, this is how you solve problem 2. What about problem 3? Problem 3 is not that difficult. It is e to the power log x plus 2 then plus log of 1 by x plus 2 and then you have plus x equals to 3. This can be rewritten as x plus 2, this can be written as minus log x plus 2. I just because x plus 2 to the power minus 1, so I written is minus log x plus 2 plus x equals to 3. This would become 2x plus 2 minus log x plus 2 equals to 3. Oh, sorry. So, this would be actually difficult because here you have log term, here you have x term, right. So, this is not easy. Maybe I can change this problem slightly. So, let us say this is, let us say e to the power x plus 2. Let us say this is e to the power x plus 2 here in the denominator. So, you can rewrite it as minus log e to the power x plus 2, which can be written as minus x plus 2, okay, equals to 3. So, what you have is actually x 2 will cancel out, x equals to 3. That is the solution. All right. Now, I want to give you some functions, and your goal is to figure out domain and codomain of this function and try to draw the graph of the function. Okay. So, first function is log of, let us say x divided by 1 minus x, log of x divided by 1 minus x. There is actually name for this function, this is called a logit function. Okay. So, this gives you log odds of something. Okay. So, let us figure out domain, codomain, and let us try to draw the graph of this function. How would you figure out domain of this function? Okay. What is domain? All possible values that the input variable x can take. Okay. So, what possible values x can take here? Well, this is a logarithmic function. So, that means anything inside logarithmic cannot be 0 or less than 0, it has to be greater than 0. So, x divided by 1 minus x has to be greater than 0. Also, this denominator here cannot be 0, otherwise anyway it will not be well defined. So, x cannot be equal to 1 and this entire thing has to be greater than 0. So, can we try to do something about it? Well, if this entire thing has to be greater than 0, okay, this is possible only when one thing that has to happen is, if you take this on this side, so x greater than 0. So, x should be greater than 0. Another thing, let us say x is greater than 0. Okay, let us say x is positive, but can it be a large positive value? Not possible, right? See, the term is x divided by 1 minus x, right. So, if let us say if x is negative, okay, if x is negative, then the denominator would become positive, but the numerator would remain negative, and that is not what we want. This value, we do not want this value to be negative. We do not want this x to be 0 as well, because if x is 0, this will become 0, it can't be 0, right. So, we do not want 0 as well. What if x is 2? Let us say x is a large positive value, or let us say 100. Okay, so, what would happen in that case? In the numerator, you would have a positive value, but in the denominator, you will have a negative value. Okay. So, every time 1 minus x, let us say x has some positive value, and 1 minus x is, let us say, less than 0. Okay. In all those cases, your denominator will be negative, and although the numerator is positive, so this will not hold. So, this is not possible. So, what does that mean? Your 1 minus x should be, when x is greater than 0, then 1 minus x should also be greater than 0. Okay. And in what situation this will be possible? When x is less than 1. Okay. Anyway, when x is negative, this anyway does not hold. This will hold only when x is positive, and only when 1 minus x is also positive. Okay. And that can happen only when x is less than 1 as well as x is greater than 0. So, x has a value strictly between 0 and 1. Okay. X can be 0? No. Can x be 1? No, this is already ruled out. So, x has to have a value strictly between 0 and 1, but not equal to 0 and 1. Okay. All right. So, that is the domain of this function. So, x can take a value between 0 and 1. What value this function can take? What would be the codomain? Well, this is logarithmic function, where x can take any value between 0 and 1. So, basically in principle it can take, because it is a logarithmic function, so it can take any negative positive value. So, let us say f of x, that codomain is such that it is set of all real numbers. Okay. And how the graph would look like? Remember, x can only take values between 0 and 1. So, let us say here you have 0, here you have 1. At 0 it is not defined, at 1 it is not defined. Let us say what would be the value at x equals to 0.5? When x is 0.5, you would have 0.5 here, 0.5 here. So, inside log you have 1. So, log 1 is 0. So, x equals to 0.5, the value of this function is 0. Okay. And what would be the value of function at slightly larger value? Let us say 0.75. So, at 0.75 in the numerator you have 0.75, in the denominator you would have 0.25, it is log of this, right. So, it would be log of 3, which would be a positive value, but if you take x equals to 0.25, then it would be log of 0.25 by 0.75. So, it would be a negative value, and exactly same negative value, minus log 3, as opposed to x equals to 0.75. Okay. So, it would look something like this. So, at x equals to 0.75, the value of y is somewhere here, and x equals to 0.25, the value of y is negative and somewhere here, like this. Okay. Maybe not as bad, something like this. Okay. So, it turns out as you keep increasing value of x from 0.5 to 1, the value of y will keep on increasing and will sharply increase near 1. And on the other side, as you keep decreasing the value of x on this side, this will keep decreasing and will sharply decrease and go towards minus infinity. Okay. So, this is how the graph of this function looks like. Okay. Similarly, this is an exercise for you. You can try to find domain and codomain of this function. Log of 1 by 1 minus x square, find the domain and codomain and draw the graph of this function. Okay. So, let us, just to give you a head start, how do we find the codomain? How do we find the domain? Okay. To find the domain, we know 1 minus x square has to be greater than 0. Okay. Can this denominator be equal to 0? No. So, 1 minus x square can't be equal to 0, and that means x can't be equal to 1 and x can't be equal to minus 1. Okay. So, that is one constraint, and this entire thing has to be greater than 0. Now, 1 is already greater than 0. Okay. So, that is not the problem. Denominator is the only thing that can cause a problem. So, if denominator is negative, then this relationship, then this constraint would not hold. If denominator is positive, this will hold. So, denominator has to be positive. Okay? That is the only way this would survive, right. So, for denominator to be positive, x square has to be less than 1. Okay. And in what situation x square would be less than 1? Can it be a large positive value? Can it be a large negative value? No, right. So, x has to have a value between minus 1 and plus 1. So, if it has a value between minus 1 and plus 1, its square root, its square would be less than 1. Okay. So, your domain is like this, x has to have a value between minus 1 and 1. Now, we can draw the graph of this function. Let us go back to our logit function, which was log of x divided by 1 minus x. Can you find the inverse of this function? You need to find the inverse of this function. How do we find inverse? First, let us replace f of x by y. So, this becomes log of x divided by 1 minus x. Let us try to solve this for x. Can we solve this function for x? Let us give it a try. So, if I take exponent on both sides, this would become e to the power y equals to x divided by 1 minus x, right. Now, I can rewrite this. How? I just need to reduce these terms into a single term of x. So, let us say I divide both numerator and denominator by x. So, in the numerator it would be 1, here it would be 1 minus x minus 1. So, I can rewrite it as 1 minus x minus 1 equals to 1 by e to the power y. So, 1 by x is actually 1 plus 1 by e to the power y. So, 1 by x can be written as e to the power y plus 1 divided by e to the power y, and x can be written as basically inverse of this, e to the power y divided by e to the power y plus 1. So, that is the inverse function. So, if you want, you can further simplify it. This would, if you divide it by e to the power y both numerator and denominator, this would look like this, 1 by 1 plus e to the power minus y. Now, to get the inverse function, you can replace x by f inverse x and you can replace y by x. Okay. So, this is the inverse function of our logit function, f of x equals to log of x divided by 1 minus x. Okay. So, this is the inverse function. Now, this inverse function is called actually the sigmoid function. Okay. And this is a very useful function in logistic regression, in machine learning, in artificial neural networks, and reason is this: what this function does, that if x has any real value, does not matter what real value, x can have any value between minus infinity to plus infinity. So, x could be any real value. For any real value of x, this function, this f inverse function would always be constrained between 0 and 1. So, basically it converts any real value, it transforms any real value to a real value between 0 and 1, okay, which you can actually use to assign probability to some event, right. So, that is why this is very useful. Okay. So, this is the codomain of the function is 0 to 1, domain is it could be any real number. Remember, the domain of the logit function was 0 to 1, here the codomain of the sigmoid function is 0 to 1. So, the function looks something like this. X can take any real value, right, but y is strictly between 0 and 1. So, let us say here you have 0, here you have 1. Okay. So, it looks like this. So, it increases and then becomes asymptote at 1, and on this side it decreases and becomes like this. Right. So, this is the graph of sigmoid function. Yeah. Now, this is one of the important functions. Now, coming to applications, which I will just briefly discuss. Now, the sigmoid function is one of the major application that we often apply to activation functions. We often use it in artificial neural networks. For example, you want to categorize some pictures such that let us say you give a neural network a task that it should identify whether the picture contains a pen or not. Okay. Now, the model would work in such a way that it would use all those feature weights, let us say some neural weights, right, and using those feature weights it will try to assign some real value to the likelihood of having the picture, having the pen in that picture or not, and it could be some large negative or large positive value, but we want to convert it to probability, so that we can probabilistically decide whether this is a picture of a pen or not, right. So, that is where sigmoid functions are very useful. So, these are nonlinear functions that transform activation into probability. So, think of x as some activation and f inverse x or this function would take some value between 0 and 1. So, that is probability. So, this is a function that can transform any activation which could take any real value to some probability value, and this is very useful also in computational neuroscience. Let us say you want to build model of let us say underlying neural architecture. So, there you will deal with activations. So, let us say certain network is more activated, certain network is less activated. You will take that activation and you will figure out probability that particular network will be accessible and whatever you want to do with that, right. So, that is one kind of function that is extremely useful, sigmoid function as well as logit function. Logit function is used in logistic regression, and similarly you can find these negative exponential functions. So, let us say there is some node in the network which has some activation A at time t equals to 0. Okay. Now, activation in both let us say long term memory as well as short term memory, it has some decay. So, activation always decays, right, with time. So, we can let us say write its decay function. It could be some exponential function, let us say decays with this function e to the power minus t. Okay. So, it is exponentially decaying with time. So, as time increases, this activation will become smaller because it is decreasing with this function like this. Okay. This could be a different function as well, some other form of exponential function. You can also determine the rate of decay if you just write some term here, let us say e to the power minus at. Now, a will determine the rate of decay. Okay. So, we see such functions all the time in activation decay, in interference. So, in all these memory models, right, how things are encoded, right, there we find these logarithmic and exponential functions. These functions have a lot of utility in let us say population growth models. So, if you want to model growth of bacteria or growth of something in a population, there we use exponential functions. Logarithmic functions again are useful for let us say if you want to define logarithmic decay, or as well as to figure out how much residual activation is there, right. So, how much, so let us say you stored some memory and it has decayed for a long time. So, how much residual activation would be there. It can also be used in perception and working memory models, right. So, we will see some examples later on if we discuss some of those, right. But these two are very important functions, and you will often see them in research papers and in your coursework. Okay. So, all right, I will stop here with this important week on logarithmic and exponential functions. Next week, we will start trigonometric functions, which are also some important functions which may or may not be very useful for you, but some of you would definitely find them very useful, especially the people who want to work with dynamic models in cognitive sciences, right. So, I will introduce you to trigonometric functions in the next lecture. All right, I will stop here. Thank you.